Good morning, everyone. This talk is about finding anomalies in 10 seconds. Mass waiting for new threads at the Google Play scale. It is a joint work among Indiana University, Institute of Information Engineering, Chinese Academy of Science, and Penn State University. Now, there are billions of mobile computing devices in the world. 70% of them are Android devices. According to a report in 2014, 99% of mobile malware targets Android malware. So we feel that malware detection is urgently needed. Current approach for detecting malware are usually signature-based or behavior-based. These works are extended from the detection approaches in PC area. Are they effective in detect malware in Android world? We know that signature detection cannot detect new malware. However, according to a report, there are over 160,000 new malware samples created every day. And don't forget code obfuscation. For example, Droid Cameron can directly work on Android bytecode. How about behavior-based detection? They usually use heavyweight information flow analysis. It also requires to know the suspicious behaviors, such as dynamic coding loading. If the behaviors are not known previously, behavior-based detection cannot detect it. So can we design an approach that is first highly efficient? Second, can detect malware with unknown behaviors. We achieve this goal using neither signatures nor behaviors, but only code comparison. We found there is a special business model that is quite different from that in PC world. In Android world, attackers like to attach the same attack payloads to legitimate apps, but not implement a new app with malicious code. If they implement a new app, on one hand, they will spend lots of time in developing and lots of effort to distribute the app to impact more people. On the other hand, when the app is found to be malicious, all the infected user will be lost. For the attackers, why not directly use a famous app to infect more users? In this way, even if the app is found, the attackers almost lose nothing. When we think about the business model, we found there is a unique drawback that we can take advantage of. What we do is to simply compare the code of related apps. The related app means that an app and its repackaged version, and those repackaged from the same original. And if we find this case, we can change their different part. If a different part are not libraries, we think that highly suspicious. We also check those apps that looks unrelated, those of different origin signed by different parties, and to inspect this comma code. Is it strange that the comma code not library? So we can check it and find that if there is some suspicious activities inside it. These segments, once found to be inexplicable, are almost certain to be malicious. Regarding the related apps, we check whether they have similar views. Views are user interfaces. We use views because if attacker changes the views, it may change user experience and let the repackaged app to be different from the original one. In the end, the malicious app will be taken down by the market. If two apps' views are same, we analyze the code differences. Otherwise, we check the code intersection. This Diff analysis is well suited for finding previous unknown malicious behavior and also can be done efficiently without resorting to any heavyweight information flow analysis. A view is user interface. It contains one or more visual visuals such as buttons, list views, text views. This UI components responds to user input events. For example, if we click some buttons and the view will change to next one. And if we connect more, and the views will change to some more views. So let's see. Yeah. In our ridge, we model such a UI structure as a view graph. On such graph, each node is a view, and the arcs connecting the nodes describe the navigation relations among them. According to the types of events, such as on-click, on-focus change, on-touch, edges can be different from each other. When there are more views, we add the corresponding nodes to the view. If the views are triggered by another entry point like this, we could create another view graph. So for some apps, they have more than one subgraphs. Then we can compare two apps using the view graph. When two apps look similar, their view graphs are very close. However, simply using isomorphic algorithm to compare two view graphs is not scalable. It may take over 100 years for compare 1.2 million apps. So how to deal with this problem? Can we avoid graph isomorphic analysis? If we can use a dimension compression, for example, use a number to represent a graph and only compare the number, then we can use binary search for quickly comparison. The first thing comes into our mind is using several features to represent the graph. But how to select the features? When we view the graph, it looks like a physical object. So can we use the mass center to represent it? The mass center is a point. And when the graph changes a little, the mass center will also change a little. So is it possible to use such point for comparison? For this dimension compression, we meet two challenges. A graph edge is an abstract relation. The abstract relation could have arbitrary length. This will make the graph or a physical object look different. The mass center is also be different. The second graph here shows an example. Actually, it is the same as the first one. The second challenge is that switching branches changes node positions. The third graph shows an example here. Although it looks different, it is still the same one as the first graph. So our idea is to fix the node in the graph. The first step is to map a view graph to a 3D view graph. And we can generate its mass center of this 3D view graph. Then in the second step, we do a scalable comparison. A 3D graph is a view graph in which each node has a unique coordinate. The coordinate is a vector xyz. X is the sequence number in the view graph. Y is the number of outgoing edges of the node. Z is the depth of loop of the node. This is an example of a 3D view graph. Then we can compute the mass center of this 3D view graph just using a basic physical formula. We call it vcall. We put the vcall for each graph into a database and sort them. Then we can first compare whether two subgraphs are the same using the distance between two corresponding vcalls. We then do map app level computation to see how many subviews in one app is the same as those in another. This comparison has two benefits. The first one is the similarity between two graphs is monotonically correlated to the distance between two vcalls. When a graph changes little, its vcall will not change a lot. The second benefit is vcall are sortable. We only need to compare a vcall with its neighbors, but not all centroid. So we can do a localized global comparison. After we get two apps with the same view and different signatures, signature here means not the certificate used by authors to sign the app. The difference method between the two apps may be malicious. Since we need to find the difference method, we need to first compare method. How to do this scalably? And are the difference method really malicious? Facing the first challenge, we use similar idea on view graphs. For each method, we can get its control flow graph. Then we generate a mass center for this control flow graph. Still, we need to map the control flow graph to a 3D control flow graph and perform dimension compression. We call this math center as M-core. In this way, we can compare the M-cores among different methods. To solve the second challenge, we need to identify benign code in the intersection, such as ads and other libraries, updated code, and unharmful code. We first use a whitelist to remove library code in the intersection. We judge whether the diff path has some relationship with the intersection part, such as caller-callee relation. We call it a standalone test. The rationale is that repackaged apps are the mainstay of Android malware, and the malicious payloads are often injected automatically, using tools like Smiley or Backsmiley, without any significant change to the code of the original app, which can therefore be located by looking at the diffs between the apps of the same repackaging origin. To identify the unharmful code, we see whether the diff part contains sensitive APIs. In this way, we can avoid heavyweight information flow analysis. When two apps have different views, we need to go through an intersection analysis. Again, we need to check, are the two apps really unrelated? Is the common code really malicious? So if we face the first challenge, we can use similar ideas with diff to solve this challenge. How about the second one? Is the common code really malicious? For the library code, we can use whitelist to remove them. How about the code reuse and templates? This is different from the diff part, and we cannot use the library to solve this problem. So we use a training set. We get the method intersection and submit them to VARSTotal. The training set is randomly selected from our dataset, 1.2 million apps. And we get the intersection and sum them to VARSTotal. If VARSTotal says that there's no problem, we think that they are clean. Then we can report the suspicious code, the method with dangerous APIs. Here is the evaluation. We use around 1.2 million apps and remove duplicates using MD5. The market covered is 33 markets. The number of apps are collected from different markets and regions, like from Google Play, from Chinese market, European market, and the market from United States. We collect about 400,000 apps from Google Play. Then we submit this app, we test the false positive. How to test it? We mass-wide, our system has detected about 127 apps as malicious. We then sub them to VARSTotal. VARSTotal is a website, is a public website and hosting 54 scanners to scan whether an app is malicious or not. The scanners include some famous ones like Norton, McAfee, Kaspersky, and others. After that, we find the false detection rate, that is false positive virus all detect is 4.73%, and the false positive rate, the false positive virus all apps analyzed is less than 1%. Then we manually studied the apps that viewed by VARSTotal as clean. We find that 20 out of 40 are really malware. They use some sensitive API and they download some apps and install it, and all they seriously take pictures and send it to a remote server. How about the coverage? We random sampled 2,700 apps from our 1.2 dataset, and we sub them to VARSTotal. VARSTotal says there are 281 apps are malicious, and our system as well detected 197. It takes 70% of them. And it's unfair to compare our system with the whole VARSTotal. This is because VARSTotal hosts 54 scanners. So we compare our system with individual scanner in VARSTotal. We detect the most number of malware among these scanners. The second one is not a 32. It can detect 60%. And how about others, like McAfee? It can detect 16%. And some other, like Norton, it can detect less than 16%. And note that there are 21 apps missed by VARSTotal. And we also test the performance. We use a very powerful server. that with 260 GB memory, 40 cores, and 28 TB hard disk. It takes less than 10 seconds for this detection. We find 35,000 apps from North America, 4,000 from Europe, and others from Asia. And 7.6% of the apps from Google Play are potentially harmful. While among the apps detected by virus total, 41% were alarmed by at least 25 out of 54 scanners. Also, we find some markets like Google Play do have some make effort to mitigate the malware threats. Most malware we discovered were uploaded in the past 14 months. Before that, there are almost no malware. Then we also have some other findings. We find a mystery app disappearance in Google Play. After uploading 3,711 apps to virus total, 40 days later, 250 apps disappeared. 90 days later, there are another 129 apps disappeared. Among these disappeared apps, 54 apps, that's 14% of them, are detected by virus total. This is easy to understand. That virus total can give the result to Google. We know that Google have already bought virus total. Then we'll do another round of measurement. We track the 2,265 developers of the 3,000 apps for 4 months. The additional 2,014 apps disappeared, and they all detected by malware. But note that we did not check them by virus total. Why? But we find that some of the apps are detected by virus total. This is the apps that maybe virus total tell Google. We find Google also looked into their common malicious components under the same developer. That means if Google finds one app malicious, and Google can check all the other apps belonging to the same author, and to find whether it is malicious. But this check cannot across the whole market. This is because it may take longer for them to do so. The cost is very high. And our work is just the one that can help them to do this in a few seconds. We also have other findings, that is the reappeared apps. We find 604 confirmed malware. It takes 28% of them shows up in Google Play again without any change. They have the same name and same MD5. We find other 829 apps shows up using different names but with the same MD5. They have high impact of the malicious apps. About 400 of them has already been downloaded over 1 million times, and 2,000 apps have been downloaded over 50,000 times. And they have very high rate. 3,000 apps has a rate of 3.9. Another interesting thing here is some signatures are used very often. The top one is used over 1,600 times. It means the malicious author are very productive. We also check their identities, the developer names, which should be different for each author, but we found some signatures are used by lots of identities. This is so strange. Maybe the author has lots of money to register for many identities. So this is the conclusion. We propose a new technique for efficient vetting of apps for unknown malware. We compare an app with all other apps on the market, Diff analysis, lightweight code analysis compared to other approaches. We implemented this system mass-wide and apply it to analyze 1.2 million apps and found 127,000 malware. 20 like to be their days. So before the end, I want to show our system. We want to make a public service of this system and want others to use it. Now I can show a simple demo here. Let me see. Okay. This is our system, but I cannot see it. Let me see whether I can do a copy more than. Let me see. Whether I can see it. Okay. So here we can upload the APK file here, for example here, and computing some hash. And since it has been analyzed before, so we will last analysis report and also analyze it again. So this is similar to what's total. Here we analyze again, and it shows the results. It's quick. So the result not only shows that the app is found to contain potential harmful code, but also shows why the app we view it as malicious. For example, here we can get the method name is getPhone, and it uses some sensitive API here, get line number, and also the class name is also suspicious. It's bot and setting. And for others, we can find another app, another method. It use get original address, use in SMS message, is on receive. And this is also in this bot class name. So this is our system. So please try it. And this is a prototype. So it now can support IE and Chrome, but we will add support to Safari later. So this is also our system website. Okay. Oops. Okay. Thanks.
Zhang, Microsoft Research. Great work. So I have a question about your UI structure graph. So did you use dynamic analysis, or runtime, like this random monkey clicking to generate this UI graph?
We generate graph use the widget in the view graph, in the views, that user interface. Widgets is like the buttons and like some other lists or something. And it will also track the click events. If user click one button in one view, we will add a node to the view graph and connect to two user interfaces. And the connection is the edge of this graph and shows that what is the event that triggering this.
Right, so someone clicked those
And
buttons?
it's not only clicks, there are some others like drag or some move or two fingers. We have other events. It's not
so
only.
how did you generate those events?
Oh, generate events. We scan the binary scan the byte code and find there may be some user events inside the code, so we can get this.
So you use a static analysis?
Yeah, we do static analysis.
Right. So we used similar techniques last year using security paper. So the difficulty is to sort of find that code that binds the UI element, right?
Yeah,
so
we can do that.
It could be embedded in XML, or it could be embedded in the code. So
Yeah,
there are lots
so
of places.
yeah, so this is the reason we use this subgraph. So there may be several entry points in it. So we need to first find the entry point. Then we can track the code inside this entry point and do a forward tracking. All of them are done statically. So we can do that.
Okay, so but then one last question. So
Okay.
did you check the coverage of your graph? So like a few sort of apps did you see how accurately your graph reflects the real UI?
Yeah, we track most of the code, and static analysis have this problem. It cannot track all the paths in a code. So we do our best to coverage more of the code and try to represent in our view graphs.
If no other questions, then one more. So
okay, sure.
So the difficulty is if there's a login event or anything that is hard to sort of create an edge between these nodes. Wouldn't that be easier for those adversaries to embed attacking code like after those login pages and so on?
I know that.
So
Yeah, attacker can do that. But if attacks do that, that will impact user experience. The users may find it, and this app will look strange. And for attackers, he may want lots of users to use his app. But if the user experience change, users may find it a very strange app and let others know it's strange app, and user will not use it.
Okay, all right.
Thank you.
Hi, Chen from Shanghai University. So, do you assume that all apps using the standard UI component, can you handle the case where the app using some customized UI?
Yeah, we can handle it.
Okay.
There are some customer UI. If they use customer UI, the customer UI will inherit from some other UI. Like from a basic class, we can do that. And we can first track the father UI. And we can find the inheritance relationship, so we can find the customer UI.
Okay, great. Thank you.
So I have one last question.
Okay.
So your results were that you can do this very, very fast in less than 10 seconds, but how much time was needed for the pre-processing? Because it seems like it's a very hard task to go and extract all of this.
It's already included in the 10 seconds.
It's
included in the 10 seconds for the pre-processing, like generate view calls and generate M calls for one app. But we already do some other things like generate 1.2 million to generate view graph and generate M calls for the 1.2 million. This is the process we already do that and put it into the database. But for user uploaded one app, and we generate them and do this comparison and all the search. This is all in this 10 seconds.
Thank you. Let's thank the speaker again.
Thank you.